Okay, so let us dig into more details about constructing a categorical tree. So let p hat mk be the proportion of training observations in the mth region that are from the kth class, right? So we have m regions, something like R1, so R2, say m capital regions. These are our regions, decision regions, and we have classes 1, 2, and so on up to k capital. For binary classification, k capital is k. Now, p hat is the proportion of training observations in the mth region that are from the kth class, right? So it means that the actual prediction is going to be what is going to be. So we're going to maximize, to find the maximum of p hat mk over all k that are between 1 and k. This is going to be the probability of the most probable class, and the argument argmax is going to be the corresponding value of k, and this is the prediction. Right, so now cross entropy for a particular region. So this is the cross entropy. So this is a cross entropy for just one region, for region M. It's not the entire cross entropy. It has this funny formula that kind of resembles the familiar cross entropy, but it is also different. So let me explain why this is actually the same thing as the familiar cross entropy for logistic regression. Right, so what is the familiar cross entropy for logistic regression? So this is minus the sum of the actual value of y times the logarithm of the predicted value of y hat, minus the sum over 1 minus yi times logarithm of 1 minus yi hat. So this is the familiar cross entropy for logistic regression. So why is it the same thing? So notice that for a categorical tree, for a given region, within one region, all predictions are the same, right? So for all training set of observations that belong to the same decision region, they are classified in the same way, and the prediction is the same. So which means that these terms with y hat can be factored out. So if we take the sum over all observations belonging to the same region, then we can just take it out, factor it out, and this is going to be a logarithm of yi hat times the sum of yi for the given decision region. So with a minus sign, so minus a logarithm of 1 minus yi hat times the sum of 1 minus yi. Okay, but these y's are zeros and one. I mean, for logistic regression, so where we introduced this cross entropy, these y's are zeros and ones. So this, and if they are zeros and ones, this sum really means that this is the sum of ones. So this is just the number of ones in the region. So in the region Rm. By the same logic, so this is the number of zeros in the region Rm. All right. So and this is actually our logarithm is actually minus logarithm of yi hat. It's just the probability. So this is actually the probability that given the that we are in the mth region, so we classify our observation as 1, and this is logarithm of p hat of, because of the same logic, m0 with a minus sign, right? So all the terms are here. So the only difference is that here we have probabilities, right? And in the familiar cross entropy for logistic regression, we have a very similar sum. So only instead of probabilities, we have numbers. So the number of observations. So what it really means is that if this is our cross entropy for a particular region, so the familiar cross entropy for logistic regression is going to be this number times the number of observations, say absolute value of Rm, is going to be the number of observations in that region. So if we multiply this by the number of observations in the region, then we will get the familiar cross entropy that we learned in lecture 1 and lecture 2. Right, so adding this over all the regions, we will get the familiar and cross entropy for the entire data set. Right, so if we the familiar cross entropy, the total cross entropy, so total cross entropy is the sum of this d cross entropy for a particular region times the number of observations in that region. And the sum is taken over all the regions. Okay, so this is the cross entropy. So the new cross entropy and the familiar cross entropy, they're really the same thing. Now, so what is this Gini index? So the Gini index is actually very similar to this cross entropy. It's just that for the cross entropy, it is motivated by the fact that this is the maximum likelihood for a logistic regression. But here we do not have a logistic regression, so we have a categorical tree instead. And the question is, so why bother with logarithms if we can make it simpler, so to say? And the way we make it simpler is by recording that a logarithm of 1 plus x is approximately equal to x, right? So this is familiar from calculus 1. Well, so which means that a logarithm of our p hat k which is equal to logarithm of 1 minus p hat of mk. So this approximately equals, so this becomes my x. So this becomes minus 1 minus p k hat, approximately equal. And this is what this term is replaced with in the Gini index. So it just works very similar. So the only advantage is that it doesn't have logarithms. So what they do is they use either this cross entropy or they use the Gini index. It's a bit tricky to figure out which of the two is used in each particular library in R. So you probably have to do some experiments, but it doesn't matter. So the final result is the same because it's almost the same thing. So they either use the cross entropy or the Gini index to grow a tree. So meaning that every time they make a new split, so they make a new split as to maximize the reduction in either cross entropy or the Gini index over the whole training set. And for pruning a tree, they are going to use classification rate instead. So this is a bit of a difference between categorical tree and regression tree. So for regression tree, they use the residual sum of squares for both growing a tree and pruning a tree. So for categorical tree, so they use cross entropy or Gini index for growing and classification error rate for pruning a tree. So a decision tree has a number of hyperparameters that I guess you could hypothetically fine-tune with cross-validation, but no one really does that in practice. But hypothetically, there is a number of hyperparameters, so it's just for your information. And what is important to understand is that variable importance can be measured as the drop in cross-entropy or Gini index, depending on which of the two is used, due to splits in each variable, all right? And this variable importance, it can in future be used for variable selection. So this is all about decision trees. And now we are going to continue with ensemble methods.